Hello, welcome to Automat live coding. So you may have seen Automat before. We have performance problems in Automat, big performance problems. When we run Automat, you can see that when it stops, we can probably stop that. So let's stop all of those objects that are kind of dancing around here. You will see that after a moment our FPS shoots up. Okay, I was messing with the rendering pipeline, but actually that's good. You can see that the rendering is super slow. Oh yeah, even when I was changing the size of the window, it's just awful how delayed, the signals are now. And the reason for those issues is fairly simple. If we look at VS Code, at our sources, here we have connection widget, connector optical, and somewhere here we have a function called blah 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 draw cable. Right? This is the function that we are calling every frame for every cable that we want to render. And look at that. Whenever we draw a cable, we take those shaders. Here is a vertex and fragment shader that's going to do the shading, so that we get a nice 3D texture. And we compile it. And we don't just compile it every frame, we compile it for every cable that is being displayed on screen. So right now, when we have just one cable on screen, even though it takes, for example, the full screen, so the fragment shader executes for every pixel on the screen, the latency is still decent. It's like 50 frames per second. It's bad, but it doesn't matter how much pixels we are drawing, the speed of rendering is basically the same. So this tells us that the performance issue, is not proportional to the number of pixels which we are drawing. Actually, when we just move out, when we stop showing the cable, the FPS increases again. It's still not amazing because we still have those objects here in the toolbar. They are all rendered each frame, so they are still slowing the rendering. But whenever a cable appears on screen, like now, we have 2 cables, 4 cables now, and the FPS just tanks. And this is because we just shouldn't compile those shaders for every cable on every frame. And there is actually one more shader that we are also compiling here. If we go back to the draw cable, in addition to this shader, we also have this new mesh, irrelevant. We had one more shader that we are also compiling. Oh yeah, maybe here, maybe this one. So, the solution seems to be simple, right? We should just cache them and the FPS will recover. Not quite. Actually, it's good to have a small performance issue because, as you can see here, our performance issues, they don't come from slow hardware. They come from bugs in the code, right? And the only way to fight against those kind of bugs is to actually insert systematic protections that will ensure that going forward, those bugs, Automat should be able to deal with those kind of bugs because they will happen in the future. There will be much more of those performance issues. We cannot have one poorly implemented widget, just this connection widget, to kind of pull the whole system down. So this is actually good. This performance problem is good because this allows us to implement a proper system for dealing with those kind of issues. A sort of mechanism to deal with slow widgets. So this slow rendering is actually causing a little bit of a problem because Automat is meant to drive other applications. So it's meant to send signals to external programs. And it's really going to be super slow because we are right now single-threaded. So the rendering has to compete with event delivery. And that means our event delivery is jittery, we have a high latency. We can actually run the test. Let's do a test. So this is actually an automated test which checks how consistent Automat is at event delivery. When it finishes, we can see the graph, and it tells us that there is a jitter between event and event. So all of the events should be delivered on this straight line, but the actual delivery is offset a little bit. I mean, it's quite a lot actually. So every second we are losing 2 frames. And the jitter, like from frame to frame, is also massive. It's like 2.5 frames. Real bad. Real bad. So we already have this benchmark, so we can see the results of our improvements. So now we can iterate on the solution. So let's start by looking at our frames. So this is how we can think about our rendering tree. So we have a root widget, which is usually a window. I think I had a nicer graph somewhere. Maybe here? Yeah. So we have a root window, which is a widget, and it draws other widgets. And they draw each other recursively. Each widget that we draw, we made this arbitrary decision that we will cache them in textures. So when the widget doesn't change, we can reuse the previous texture. The textures don't use a lot of memory, but they save a lot of compute. So buttons, as long as the user doesn't touch the buttons, we can cache them in a texture. If the buttons don't change, then the whole hotkey object, which aggregates a bunch of buttons, can be cached in a single texture. And the objects which are just staying in place, they can just happily live with their textures. Or toolbar. As long as we don't touch the toolbar, it's essentially a texture that we can bleed on screen. Okay, when we actually try to put some numbers on those widgets, we will see that rendering each of them, we actually did this measurement during the last stream. We will see that it looks something like that, where each widget takes some amount of time. And let's say all of them take 6 milliseconds to render. And those can take 2 milliseconds. So we have those expensive leaf widgets and slightly less expensive intermediate widgets the top level widget, which we are rendering, the window, is actually super cheap to render. This is just the background and the compositing of a couple textures. So, first thing that we should realize is that there is no way to render all of that in 16 milliseconds. So 16 milliseconds is a budget. But 60 milliseconds is actually already a pretty high or maybe low bar, because really the type of rendering that we are doing, it's so simple, it shouldn't be that slow. We should be able to render this at much lower latency, so that it should be usable in VR, where we need something like 4 milliseconds. So VR, yeah, roughly 4 milliseconds. But even in VR, 4 milliseconds is often not good enough. Like we still want to go faster than that. So we need to find a proper solution to render like at ridiculous speeds. I would be happy with 1 millisecond. 1 millisecond is something that there was this old video about, super old, about impact of latency on touch and kind of delay. There was a video, it was super old. I don't think I will be able to find it. Yeah. But basically, even at 10 milliseconds, you can, if you have a touch screen and you drag something and there is like a 10 millisecond latency, you still see this kind of stuff. You don't see this with mouse, right? Because my mouse is rendered by computer. But if I actually touched the screen and moved my finger there, you would see how kind of disconnected all of this is. So the rendering has to be fast. Because we don't just, like when you move the mouse and you see the mouse cursor already has some latency. You rarely see this, but it's there. And it really feels nicer to have less latency. So this brings me to the goal. We should formulate our goals for our rendering pipeline. So when we are talking about real-time systems, we often differentiate between hard real-time and soft real-time. In our case, this is soft real-time. We just want to go as low as possible, because the lower we go, the better feeling we are going to produce for the user. So fastest response time possible, this is our goal. Then we also want to be robust to stuff like our connection widgets. So a single terribly implemented widget shouldn't bring the whole UI down. This is important. And lastly, there is also another type of performance issue which is completely different. So even if we optimize Automat as much as we can, it renders in less than 1 millisecond. Slow widgets don't cause problems. There could be no slow widgets. We could imagine a system where we have only properly implemented, super nice, super efficient widgets. There is still the possibility that the system that we are running on, that the system which is doing the rendering, is just not able to keep up. We could be rendering on a potato. So we also need to gracefully degrade on, heavily loaded systems, if the system is doing some heavy processing. So this means we will need priority, so that interactive work, for example Automat, which is like in the foreground, the display window for Automat is it's very important that it renders in real time. The backend, the stuff that's behind the screen, it can be laggy, that's fine, but the stuff in foreground, this is our kind of the most important piece of the system. This has to be responsive. So UI needs to be higher priority. Preempt other jobs. We should do like all sorts of dynamic tricks to just, if we detect performance issues, we should just adjust so that those issues are not impacting the user.
Knight says,
Hello, everyone.
Hey, Knight. So those are our goals. Okay, and like I said, if we just count the time that we need to render all of the frames, and this is the case right now for Automat, we are just unable to render within 16 milliseconds even. Super bad, right? So there is one trick that games are using. The games are using this thing called downscaling and FSR. I think this is the name of this. Just super resolution. The idea is that you render at a lower resolution and then have some post-processing effect that increases the resolution back. So this is one approach, and this helps with the type of performance issues which are caused by high fragment, like slow fragment rendering. So if it takes a lot of time, let me stop this.
Yoon's IMG says,
Hey again.
Oh,
Diggs B. Stefan says,
Oh, you awesome.
yeah. So in this case, we had performance issues like treble 20 FPS, but we have 20 FPS even though we are rendering maybe, I don't know, maybe 100 pixels or 200 pixels. The cables are super small. The slowness doesn't come from the amount of pixels that we are rendering. Even if we are rendering the whole screen filled with cable. See, the performance is actually better now. It's like 50 frames per second. Or 60 even. The performance issues, when they are not being caused by fragment rendering, this downscaling isn't going to help us. So this is something I was thinking about. I basically spent the whole weekend thinking about those issues. So we could implement something like that, but it wouldn't help at all. It would be basically the same. Our performance issues are actually coming from, like, even if we render this at, you know, this scale, look, it's still terribly slow. So downscaling is one solution, and we may go this way eventually in the future. But there is another idea, which is called frame skipping. So if you look at this widget tree, we could actually try to render some of the widgets in a single frame and some of the widgets in the next frame. So this and this is 3, 9. We could also add that. That will be 15. milliseconds, and that could be 1 frame, right? And during the next frame we could render this part of the tree. This is another 15 milliseconds. This type of animation would be very different to any type of computer animation that you've probably seen in any game or any user interface. And this type of animation is actually used in some... I can probably play this. This type of animation is actually used in some movies nowadays. There is Into the Spider-Verse, which was a very popular movie, which popularized this technique.
Have you ever wondered why choppy animation sometimes feels better? Some of you out there are going to immediately
Okay, let's actually go through this frame by frame.
disagree.
Okay. Let's look at this guy moving. The quality is terrible, don't worry about that. So I'm switching to the next frame. He moved, right? And on the next frame, actually nothing happened because the video was probably recorded at 24 FPS. But the next frame, the background moves. The next frame, again, nothing. He moves, then background moves, then he moves, background moves. So there is this very unique kind of animation when things are moving back and forth. And this type of animation is actually, I saw a slightly different approach, like Into the Spider-Verse uses like even different type of animation. Into the Spider-Verse uses this approach where they render the front character and then they smoothly move him on screen, and then they switch to the next frame, and then again they smoothly move him on screen for the several new frames. So Passing the Boots and Spider-Verse, they use very subtle different animations, but they both look nice.
But think of it this way. Animation is not as simple as the frame rate of a video game. Your average video game is
Okay, let's actually watch this because this could be relevant.
Usually between 24 frames a second and 60 frames a second, but games will usually try to keep it consistent. If the game is optimized, it's always going to try and be 24 FPS, 30 FPS, 60 FPS, whatever. It stays a consistent, solid number of frames per second. But animation changes frame rate all the time without you noticing. On average, animation tends to be at a maximum of 24 frames a second, but it's rare for animation to even be at 24 frames a second the whole time. Usually it'll be half of that at 12 frames a second, and even drop down to 8 FPS or even 6 FPS. This is referred to as animating on 1s, 2s, 3s, and 4s, which is referring to how many frames the drawing is held for. Take a look at this scene from Cowboy Bebop. Nobody would call a fight like this choppy, but while most of the fight is on 2s, or 12 frames a second, there are moments where the animation is at a mere 8 frames a second or on 3s. Here's 2 frames from that fight. Look at how huge the jump is between them. These 2 drawings are held on 3s, at 8 frames a second. You can see it in the background, which is still moving at 24 frames a second. Holding these drawings for just a frame longer on 3s makes them more impactful and more readable compared to the rest of the shot, which is animated on 2s. The huge jump between these 2 frames wasn't an accident, and neither is the fact that they're held on for just a frame longer than every other frame. It's to make sure you feel those frames in the moment and feel what happens between those 2 frames. When it comes to animation, it's often more important what happens between frames more so than what's happening in a single frame. Because all that matters is how the animation feels as a whole, not what it looks like frame by frame. And sometimes what makes the animation feel better is holding on certain frames. Think about it this way. Imagine an arrow hitting a bullseye. How many frames do you think that takes? 3 frames? 2? What about 0? Nothing's there, and then it suddenly appears, with the tail vibrating into place. To me, this feels far more impactful than animating the frames in between. Because at the end of the day, animation itself is an illusion. Nothing is actually moving, it's your brain inserting the movement between those 2 frames. So the lack of anything between those 2 frames results in a far greater impact, with your brain filling in all emotion. Now, this isn't some hard and fast rule. American animation tends to animate fast movements on ones, using smears and multiples for cartoony effect, while Japanese animation will focus more on the after effects of the action, putting emphasis on what's not there in a single frame, or what comes after. Both styles can be executed well, but what you prefer is ultimately up to you. Personally, I find the quote-unquote choppy animation far more satisfying, and I think when it's done well, people prefer it that way. I know I literally just said that what you prefer is up to you, but hear me out for a second. Before the 2000s, animation made for TV limited the amount of frames drawn as an economical decision. Studios only have so much time, labor, and materials.
Okay, not interested in history. So I'm mostly interested in how this relates to this mix between
over the action itself.
choppy animation
That's why you
and
get these flashes of white in
smooth
Dragon Ball
animation.
you've been seeing that mixes the two together. Digital animation that can interpolate, but animators
Something like
choose
that.
to limit the animation to 2s and 3s for that impact we were talking about earlier. And I think this style is fantastic. In my opinion, if you were wondering why the frame rate drops in Puss in Boots 2 look so good, this is why. And it works so unbelievably well that I think this is just where digital animation in general is going. And I kind of love it. When I said earlier that people prefer...
Okay, those movies, they are using this to achieve a very specific effect because they want to render a very good kind of shot and they want to hold it for longer so you can appreciate, how stuff looks. You don't want to see everything blurry, like moving around on screen. You want to see something which is sharp that you can your eyes need time to parse, the image. And when animators do this, they actually put some thought into which frames they pick to display. This is not just random.
They want you to...
In our case, we don't have this, advantage. Our rendering system is not so clever to pick an aesthetically pleasing frame. We are going to just render widgets as fast as we can, and the choppy animation is going to be more of a byproduct of slow animation. But when we have an old frame, for example this, let's say we are rendering this frame, and we are reusing this old object, we can still blend this object because it can move on screen. So even though it's not re-rendered, the older frame can still be moved on screen and composited in a different position. So we will try to achieve a system which produces those kind of animations naturally. Not deliberately, but more as a byproduct of just slow rendering widgets.
to feel it. You don't get that from fully interpolated digital animation. And that decision making, deliberately choosing what frames to hold on and for how long, is exactly the kind of reasons why people love classic 2D animation. It gives animation a soul. A lot of people criticize Flash animation for being hollow and too digital. And while I think Flash animation can be done well, like I've mentioned before, I've always seen people praise good Flash animation when they limit the frame rate like this, because they want to feel the artist behind it, not the computer. And the thing is, doing it this way is actually harder than fully interpolated 24 frames a second animation, especially in 3D. In an article for Polygon, the director of The Bad Guys has actually described it as fighting the computer, which is a pretty good way to describe it. Animators and artists are literally fighting against what the computer gives them to add their own touch to it. Nobody's cutting corners or doing it this way because it's cheaper. It requires far more artistic input and decision making. Most of all, it requires confidence, and I think that should be celebrated. It's risky and difficult and experimental, yet confident that it works anyways. Maybe it doesn't.
Actually, this case didn't look that great. It actually looked like just picking random frames. Most animations, like the movies that he showed before, it was clear that the animators actually paid attention and selected, the best frames. And this was more like slow FPS.
Doesn't work for you, and that's okay, that's what an experiment is for. But 3D animation is still a fairly young medium that really only started 25 years ago, so we're still figuring it out. I've gone most of this video without mentioning Spider-Verse, and you've probably been vibrating in your seat waiting for it to get mentioned. But yeah, it really can't be understated how revolutionary Spider-Verse was for 3D animation. I know it can feel like studios are doing what Spider-Verse did because it's trendy, but I don't think that's the case. I think what Spider-Verse did instead was unlock something nobody realized they wanted in digital animation: to fight the computer. After 20 years of movies and TV that leaned into what the computer can do, we're finally leaning back into what the artist can do. And I think that's awesome. At the end of the day, I'm personally...
I think we got the kind of takeaway. There is another video which talks about hybrid animation. I haven't watched this one, but it seems like something that could also be relevant. I'm not going to watch this on stream. We should focus on actually writing Automat, not watching videos. Okay, so here is the plan. The plan is that we are actually going to try to pack the frames. Whenever we have a tree of widgets, only some of them often need to be redrawn. Most of the widgets on screen are already drawn. We can reuse those textures. So some of the objects in the tree are marked as invalidated. So the first thing that we will change is that when we invalidate an object and it moves, the position of the object changes. We will also invalidate its parent. That means that even if for some reason we can only render, for example, those widgets, this choppy object will still be, the old frame will be composited in a new position. So this is the first thing we will do. And we will have those partial frames. Okay, let's look at this. Okay, so we will do this rendering of only a subset. We will, for each kind of frame, we have this widget tree. We will be kind of analyzing this tree over and over repeatedly and trying to create like a good plan for the next frame. The result we will store as a graph of stuff that we want to render. Yeah, and then we will send this, ship this to client for rendering. Okay, so here is the basic graph of how this could look. Maybe I should zoom in. It's not fully visible. Okay, I will just move this on the screen. So most widgets start in this space state where they are off screen, they are not visible. So this usually means that there is no widget actually at all. Anyway, when an object appears on screen, we are in a difficult position because we have object, we don't have any surface. So the client comes to us and asks for a frame. Oh, by the way, I'm using the same rendering approach as I used in this, in another like very old prototype for Automat, where the client actually runs on the web, and when it wants to render an animation frame, it actually sends a request to the backend for the new animation frame. And the backend prepares like a list of drawing commands, ships it back to the client, and then the client draws them. So there is actually a network request on every frame. But that's fine, network requests are not that slow. Especially when we cache stuff. Okay, so here, this arrow, this means that we are going through those two steps. So the client sends a request for a new frame, and when we want to render an object, we see that, hey, there is no surface. We basically tell the client, okay, take the those drawing commands and please render the widget at a nice full resolution so that we have an initial surface to display. If the surface doesn't change over subsequent frames, maybe I can do this. If this doesn't change over subsequent frames, then we can just keep presenting this stuff. But after some time, it's possible that something in this widget is going to change. So it's going to be invalidated. It's going to be transitioned to a different state, which is that, hey, we have a surface that we presented, but this is obsolete. This is an old surface. So this is another state that the widget can be in. When a new frame comes, so the widget asks for a new frame that we want to render, then Automat is going to try to pack this widget together with other widgets. So this is a global step, this packing. It's like a global optimization step where we are trying to take this tree and we are trying to pack as many widgets as possible into a single frame. And there are two outcomes that can happen. Either we managed to pack it in the frame so it fits within the 60 milliseconds or 4 milliseconds or whatever deadline we pick, and it's going to be included in the same render, so the response time is going to be good, like very fast, if it fits in the frame. But it's possible that we measured the time and we decided that, okay, so we will render this tree, and this tree is going to be using the old frames. So this is this branch here. If we are unable to pack a widget into the current frame, we still send the drawing commands to the client. We just tell the clients, hey, after you are done rendering the frame, here is some extra work for you, so that you are not bored in the meantime. And the client can do this. The client can do this in background threads. And this way, the rendering can happen slowly over time. The client can still get like fast refresh cycle. They can work with the most of the system. But some of the slow widgets, they will just be a little bit choppy. But only the slow ones will be choppy. All right. The next thing is this transition here. So when the client is rendering something which is in the background, as long as it's rendering, we just leave it there. It can render, if it renders for half an hour, like absurd time, we just leave it there. Let it render for half an hour, whatever. When it finishes rendering, this is when the client says, when it requests a new frame, the client says, hey, please pack a new frame. And by the way, this widget finished rendering, so the surface is ready. So on the next frame, when we are packing the frame, we will actually reuse this surface, which was rendered over the last half an hour, let's say, in this absurd example, and we will composite it with other real-time rendered stuff. I mean, normally it would be just a couple of frames of latency. It is also possible that while we are rendering stuff in the background, it's going to be invalidated. And this is actually I think this is the key kind of step to handle correctly. Because when the stuff in background is invalidated, we know that the stuff that we are drawing, it's already obsolete. There is no point even finishing this rendering. But if we actually tried to drop it and re-render it, there is a very real possibility that we would never fully render the object, because some objects are just continuously animating. So even when an object is invalidated, but it was rendering in the background and it finished rendering, we will still display this old obsolete surface to the user. It's going to be delayed, but that's fine, because this is what actually will produce the choppy effect. So this is one way of doing that. There is another version, which is slightly bigger one. So this is something that also uses the downscaling trick. So we can actually render. In Automat this is actually very easy to do, because we can just scale the rendering surface. We have actually been already doing this a little bit. So when we render an object, we can just say, okay, your texture is slightly smaller than it actually was normally going to be. So we can actually, if you have objects which are very sensitive to pixel latency, like where the fragment rendering cost is very high, we can actually downscale them so that they fit within the frame and they are rendered at high latency. And this is this graph. So we have two types of renders. We have full renders, which are happening at full resolution, and we have fast renders, which are rendering at smaller resolution. And it's not binary, it's not like 1 or 0, we have either fast or full render. It's more of a gradation. We can either render this at full resolution, or we can progressively decrease the resolution towards our, I don't know, whatever kind of limit we pick.
Saxon says,
You are very smart. We love you.
Thanks, Saxon. So this is an alternative graph that we could use if we used this downscaling. So this looks very similar to this graph with full frame renders, where we have these packing algorithm and invalidations. The difference here is that once we render a fast frame, we are still going to try to pack this widget. Even though it's already fresh, it's not invalidated, it's freshly rendered, it's up to date. We will still send it to and try to pack it again, but this time we will only try to pack it as a full render, and otherwise it's actually very similar. So I still haven't seen, maybe it's because I have like a beefy GPU, probably if I try on a slower GPU we will see those problems. But I haven't yet seen the fragment being a bottleneck. So this is when we will be able to not only render stuff choppy in time, but also choppy in space. So this will be choppy in time and pixelated. So this is the choppy. Okay, so this is the flow diagram of how we want this to work like. So we have Automat, which can be running on some machine, one computer, and the client, which displays the window. It can be running in a browser on a different computer. When the time comes and we want to render a frame, we send a request to pack a frame. Automat then walks through the tree of widgets and tries to pack the frame with widgets. And we are only packing the ones which are dirty. We have some numbers here, so we can actually introduce a lag value. So this is a number, how old is some widget. So we can prioritize, for example, stuff that hasn't been refreshed in a very long time. So we can actually have some objectives here. So this is actually a rather well-defined problem. So after we pack everything, we walk through this tree of packed objects in topological order, which is from the bottom of the tree, from the leaves of the tree towards the root. And we actually don't draw the frame, and we emit the drawing commands. I was looking at Skia, and I was looking at mechanisms that we have available to do this. Skia has some pretty insane tricks for doing that, because this is actually, when I'm talking about displaying stuff over network, this is actually not very different from displaying stuff on the GPU, because GPU is essentially like a separate computer within your computer. So normally when your processor communicates with the GPU, this is kind of how this flow looks like. So the GPU says, hey, I finished rendering, and your CPU packs the drawing commands, sends them to the GPU, and the GPU takes care of rendering. And when the GPU hits some semaphores or fences, it can actually send them as a signal to the user space, so that your application can send more drawing commands and the cycle can continue. So even though this networked architecture may seem very weird, this is actually very natural for like rendering. Skia has a couple mechanisms for that. So the tricks that I am familiar with. So first of all, if we actually look at includes, there is this category called private, which we probably shouldn't use, but in Chromium, there is this deferred display list recorder, deferred display list, which, can we actually serialize this? Probably we cannot. Okay, it's unfortunate, but okay. Yeah, if we manage to pull this out, pull this off, this is going to look very, very different from any user interface that you have seen. Okay, so this is the first, say, idea. What else? We also have this thing, which is a completely separate backend within Skia, which is, so the old backend that Skia uses is called Ganesh. This is optimized, this was created a very long time ago. It's optimized for embedded systems, actually, like mobile phones, for tiled-based rendering, for OpenGL. So this is a 3D-based rendering, this is a GPU-based rendering, but it's optimized for low-end devices. So there is a new one, which is called Graphite. This is something that uses actually Vulkan. And this rendering backend, it contains this recording idea, which is just a command buffer, which is going to be submitted for Vulkan for rendering. Yeah, add commands, command buffer. And when I was reading this API is just so clean. I really, really like it. So I think, I mean, it's only a matter of time before, this is still experimental in Skia, so Graphite is still experimental, but it works. You can use it. You can even switch Chrome to use graphite. So this is another thing we could use. This would be very funny if we actually were sending Vulkan drawing commands over the network. But I mean, the graphite, the coolest thing probably about graphite is that there is actually an implementation of graphite on Dawn. So this directory. Dawn is the name for WebGPU. So this is their code name for WebGPU backend. So not only we could do this, efficiently, more naturally, but when it actually reaches the browser, it could actually render using the most efficient bleeding edge rendering API. So that would be amazing. If we go back to Ganesh, we also have some ideas here, some classes here that we could use to transfer data. Okay, maybe I don't see anything that would kind of jump out. Okay, I think in this GR direct context, oh yeah, we have some functions here that I looked at. They were very interesting because they allow us to force command submission to the GPU for images, so the stuff that we do not display. But anyway, it's something we may look at. I mean, we will look at this. So it doesn't help us with serialization of stuff, but when we actually want to execute this, because Automat is still local application, right? It's not actually networked. So for the time being, we still need to actually flash this to GPU, so we will probably use that class. So the actual stuff that we'll most likely use is located in core. So we have escape picture recorder and escape picture. Those are the stuff that we already looked at during the last stream. Oops. Close this. So we have pictures and we also have images. Those are two things that in Skia can contain deferred choppy rendering. This is how we can call this deferred. specifically lazy images. We also have those image generators, which is also another way to represent lazy images. I think those image generators, I think they are made to run on CPU, because I don't see any API for GPU stuff. Yeah. So I think those image generators are mostly for decoding pictures, let's say. Okay, and the last thing that we have is within skpicture. Here we have a function called serialize, which can actually take the whole picture and serialize it to some buffer that we can then send over. So here's an example where we have picture recorder. We record some stuff, finish recording as picture, serialize it, and then we recreate the picture from data. We could probably do... Is there something like fill text in Skia? It's also stream. I'm curious how large is this buffer. SK canvas, please. Draw simple text. And we need some coordinates probably. No, we need bytes. Text encoding, come on. And that should be it. Let's see. Blah, blah, blah. Yeah. We need more arguments. Oh, come on. it's Skia could really have a better function for drawing text. Yeah, so it's actually not that tiny, the picture that we drawn. Which is just a rectangle with a border. It's probably rendered as a path. So 8, and each of them is probably like 20 bytes, okay. Anyway, it's still something that we will probably go for. Okay, so we've been going through this. So we have, so we walked through the widget tree, we decided which widgets we are going to pack, and we serialized them in a list with some dependencies. So not a list, it's more of a DAG. So now, when we emit the drawing commands, if we want to reuse an older texture, we are drawing from an existing SK image that we have. This is a deferred SK image. And if we want to render a new object, we wrap it in a new class that we will introduce ourselves. Maybe we can call this choppy drawable. So choppy drawable has one extra function. This is called prepare, which when we actually call this, is going to produce a new SK image, which contains the freshly rendered contents of this image. So when we go through this list, for each image we are calling this prepare, or maybe flash. And once a choppy drawable is, it first has to be flashed, because during flash we can measure the time. This is important. And then when we go through the list for subsequent objects, when we want to draw this choppy image, we are actually using the SK image that it has drawn. So theoretically we don't really need to wrap it, or maybe we do to wrap it in choppy images. Anyway, the important thing is that we have to continuously measure the rendering time. When we have this list, it doesn't actually mean that we have drawn this, because we just build this list and then we serialize it and we send it to client. So this list contains, first of all, the list of choppy drawables, that are part of the frame, and list of drawables that didn't fit in. And we can also tell the client whether we are animating or not, so that it knows when to call us again. The client, when it gets this list, it immediately starts rendering the contents of the frame. And the client can do this either using, the client can do this however they want to. But it would be nice if they do this in parallel. We could use several web workers in the background, because there will be some parallelism there. So technically we could create some surfaces and then aggregate them. The final element of this list, the last one, is actually something that we will flash into the canvas after we are done rendering. Not flash, draw into the canvas. After we are finished with the frame is presented, right? So the new refresh cycle starts. We can start drawing the overflow. So this stuff that we were sent here. None of the stuff that we got here, we don't drop any of this. I'm messing up the notes. We're just doing this as we go on, until eventually time comes from the new animation frame. Because this is, let's assume this is JavaScript, so we are using request animation frame to drive the frame cycle. So we are getting the new animation frame. So we are sending the new request. In the new request for the next frame, we are including the list of all of the choppy drawables that we rendered last frame and how long it took us to render them. When Automat receives this list, we use this list first to update the render time model so we get more accurate estimation of how slow each widget is to render. And then we repeat the packing process, we send the new request. If there is any frame which is still being rendered here, because there could be frames which are still rendering, we just ignore them. We composite using whatever we can pack in the frame. Only when some of the overflow finishes rendering, it's included in the next frame request, and then we will pack it in the next frame. So this is the flow that we will use. Oops. And this is how it looks. You can check this document, this is part of the Automat roadmap. There is a section with notes, with rendering notes. Actually, part of the roadmap we can probably move over. Let's take this and paste it here. Something completely different. Let's grab this. And let's also move it to a next document. And we can drop this. This seems a little bit old. Oh, but this is the high-level architecture. This is still valid, yes, this is still very much valid. Okay. So let's switch to our roadmap and actually look at things that we could do. So I added a new point here, which is to optimize the draw cable function. This is a new thing. We should do this. We will do this after we finish the choppy animation renderer. Okay, let's break it into tasks. So let's start with frame packing. After we finish with frame packing, we can do let's say single threaded rendering. And then we will switch to multi-threaded rendering. And yeah, our goal is actually to remove all of the logs, which is actually easy to do. We just remove the logs. We don't need the scheduler, but let's first do that, because this is going to be, I want to see the impact on the jitter, and I want to see whether we can achieve this choppy animation effect. So this is the plan for today's stream. It took me more than an hour to explain this, but I guess we can get started. I think we will start at the window level. First of all, this rendering that we have right now some old nodes, don't worry about them. We are not doing stuff like that anymore. I will get rid of the picture recorder. I will comment this out. And I am going to reintroduce the old surface-based rendering. Render to surface. Because this gives us a nice times. So when I run Automat now, please stop. Please don't do this. Okay. I will actually close this now so that it saves, but it tells us that, hey, this is how long it took to render each of the widgets. On average. So on average, each connection widget takes 9 milliseconds. So we can render at most one of them per frame. Toolbar took 2 milliseconds, but that includes all of the widgets which are part of the toolbar. And prototype buttons took this much. Cool. Let's back up. Maybe even here, or not. Okay, so this is what happens when we draw a new frame. Okay, this is the top level window. Draw cached. And this it turns calls. This draw which takes canvas. So there should be two draw functions. Okay, this is the second one. Okay, so this is the stuff that actually draws the contents of the window. We should not worry about this function. We will kind of look at it from the outside. We will need kind of a different signature, I think. So who's calling this? Oops. Changed the TTY. So Linux has this shortcut. I have to log in again probably. I wanted to see who calls this function. Okay, I think this is where we will start our work. Actually, I think I will make a short break here until 1 p.m. So grab some food, and after I'm done we can start implementing this. So we will not be painting anything here. The paint function is actually going to just collect a list of drawing commands and then send it out. Yeah, so the top level is not going to get any canvas, it's all going to be deferred. Yeah, I'm very interested in how it's going to look like. Okay, see you in a couple of minutes.
Once we've done the computer graphics on the screen, the computer, with a ballpoint pen and a mechanical hand, draws what was on the screen onto an animation piece of paper. And it'll come out with a drawing that looks like this. And with a new piece of paper, I'll put on top of this, and I'll draw Basil running for his life on the gears. So it makes a nice hybrid between computer graphics.
Walt Disney Pictures presents The Black.
Disney went to great lengths to get this movie produced on 70mm film, so we are going to need a bigger screen.
Black Cauldron.
Released only a year earlier, this was Disney's most expensive movie to date, and adjusted for inflation, it's... Oh, okay, actually, that's pretty normal for an animated movie these days. But it was completely unheard of for 1985, and I definitely think it shows. Black Cauldron's animation, visual effects, and detailed backdrops are gorgeous, and in spite of that, this film was considered by historians to be poo-poo and doo-doo, thanks to some mediocre performances and discount Lord of the Rings fantasy writing. I know this movie has a bit of a cult following these days, but most people know it as The Bad One. And that really is a bummer, because it broke ground by being the first American cartoon to use CGI in its production. It also has Disney's whiniest protagonist.
Is this to be my life?
A magic fortune-telling pig. And Gurgi. So I can kind of see where both sides are coming from. While the Black Cauldron's use of hybrid animation wasn't nearly as impressive as the Great Mouse Detectives, the computer imagery on display here was still ahead of its time, mainly because they didn't try to make it obvious that it was even there. In fact, the B-roll that I've been playing for the last 15 to 20 seconds or so contains almost every hybrid CGI shot that made its way into the movie. Did you notice? I bet you didn't. But sometimes you have the exact opposite goal. Tron was a live-action movie from 1982 that was enhanced with CGI visuals that they took the pleasure of shoving right in your face. But that was always the goal. They wanted it to be obvious that it was there, and the story was written to facilitate that. The characters were in a computery world, so naturally the world looked computery. And for the time period, it was unique and novel. There really was nothing else like it. And while groundbreaking, it was considered by historians to give me a headache. Blending animation with live-action footage is a topic worth exploring all on its own, but I specifically want to focus on the merging of 3D CGI with hand-drawn 2D techniques. The reason I mentioned Tron is because in the 1980s, when people heard CGI, they thought of this, not this. The way the Great Mouse Detective and Black Cauldron were able to blend their use of computer animation so seamlessly is through a technique called rotoscoping, which is the act of meticulously tracing over source material frame by frame. Studios would implement this when they wanted to add a level of realism to their cartoons. In both movies, they specifically used it on complex shapes that needed to be viewed in motion, the exact sort of thing that would have been a nightmare to animate by hand. Back in the day, precise, sharp angles were the exact kind of thing that computers excelled at rendering. That's why they wanted CGI to enhance the hand-drawn animation instead of replace it. But Disney wasn't the first studio to make use of computers, and they weren't the only ones innovating in the 80s. Golgo 13, The Professional, was a Japanese movie from 1983 with an intro sequence that is considered by historians to have cool skeletons with guns. It's also thought to be the first time 3D CGI was integrated into a traditionally animated movie, and if you look real close, you might be able to spot where. As an animator and visual effects expert, I've spent hours analyzing this scene, and I'm pretty sure the CGI parts are the parts that look like it. If you Google hybrid animation, you'll probably see lists with a bunch of modern 3D animated movies that incorporate some hand-drawn elements, like Into the Spider-Verse, Puss in Boots: The Last Wish, and The Bad Guys. In fact, CBR.com, which as far as I can tell is just BuzzFeed for nerds, has a list called Every Hybrid 2D 3D Animated Movie Ranked according to Rotten Tomatoes. It has 9 examples, the oldest one is from 2012, and 3 of them aren't even movies. Geez, not even going to put the Iron Giant on here, huh? And look, I'm not stupid. I know that one listicle doesn't represent the general public sentiment, but for as much innovation as we've seen in the 3D animation space in the past few years, it's a little frustrating to see people act like studios haven't been trying to innovate with visuals up until recently. But I kinda understand why. As CGI started to overtake hand-drawn animation's dwindling presence in the box office, it was getting difficult to keep track of who made what. In the early days, the average moviegoer would see a trailer for a new 3D animated film, and mentally they'd either put it in the Pixar bucket or the DreamWorks bucket. Kind of like how your grandma called every video game console a Game Boy or a Nintendo. That was a bad take, cut that out. To the average, uneducated viewer, things had started to feel a little samey. There were obviously going to be outliers, but nothing your grandma was going to watch. So when something came out that was completely unique, that didn't look like anything else, and existed within an established intellectual property that people already liked, that got everybody's attention. This is why everything changed in 2018 when Into the Spider-Verse released. Well, once it hit Netflix. It was a bit of a box office sleeper when compared to all the other Spider-Man movies and was 5th place in the animation category for that year. But in spite of its moderate success story, what it really became known for was the way it blended techniques. Up to this point, we'd seen a lot of traditionally animated movies that incorporated 3D elements for added effect, or as an animation assist, or to make possible what was previously impossible. But by the time movies switched to being pretty much fully CGI, medium blending more or less disappeared, and Into the Spider-Verse brought it back. It was the first full-length movie to blend 2D techniques into 3D animation, the opposite of what had become so common decades earlier. And some say it kicked off the renaissance that influenced the sudden stylistic shift that we see in so much of modern animation. Into the Spider-Verse really did change animation forever. Except it wasn't actually the first 3D movie to incorporate hand-drawn elements and mimic traditional animation techniques. The Peanuts movie did that 3 years earlier, and I don't see no Peanuts on no listicle of every hybrid movie, so what gives? Why do people seem to think that hybrid animation started here instead of here? Well, the answer is complicated, but it all starts with, say it with me now, the number of frames per second and the decision of when to switch between animating on 2s or 3s and when to utilize interpolation techniques.
What's a cartoon?
It's frame rates. I'm going to talk about frame rates now. There should be a very obvious difference between this and this. Both are animated in 3D, but the one on the left feels way more cartoonish, and that's because the only frames you see are the ones that I posed manually. The hand on the right used all the same poses, but with interpolation enabled. That means the movements between all the poses were calculated by software and blended together with some added motion blur. The industry standard for film and TV is to display 24 images, or frames, per second. To put that into perspective, that means in a hand-drawn, traditionally animated cartoon, somebody had to draw 24 new images for a single second of video. That's called animating on ones, and it's an insane amount of work. But even the smoothest, most fluid animation you've ever seen will skip drawings as needed, because your brain is really good at filling in the gaps. A new drawing every other frame is called animating on 2s, a drawing every 3 is called animating on 3s, 4 is on 4s. You get it. Hand-drawn animation will regularly switch between 1s and 2s and 3s based on the kind of motion they want to convey. It's usually more of a stylistic decision than a cost-cutting measure. The decision of when to make a new drawing and when to hold on to an existing one is called frame pacing. So essentially, the best way to make a 3D animation look like 2D is to use poses without interpolation, with pacing on 2s and 3s, and using action lines instead of motion blur. And if I've done my job right, hopefully you'll be surprised when I do this. If you really want to sell the effect, it's not just a matter of timing. You also need to flatten out the lighting and shading. So let's take a look at some fellow much bigger than me YouTubers. Savannah XYZ might move like a cartoon, but is obviously a 3D model, where the super fluid doodly has a cartoony outline and flat monochrome colors. If you combine the two styles, you've got yourself a very convincing 3D guy who looks like he's hand-drawn, but isn't, if I do say so myself. We have a behind-the-scenes video up on our Patreon that goes into a little more depth on how we got it working, which you can check out for free. YouTube is not my full-time job, but it does eat up basically all of my free time. So if you want to support what we do here, that's the best place to do it. Just throwing that out there. Also, like and subscribe and stuff.
Cam winged. It is I, sponsorship horse.
Sponsorship horse? Couldn't have just knocked?
It was urgent. Your personal information is all over the internet. I'm here to tell you about Incogni.
Incogni? I'm already using them. And they're sponsoring this video.
Oh.
This is going to sound like I'm exaggerating, but I used to get 3 to 4 political spam texts every single day. And since I registered my YouTube channel as a business, the amount of junk mail practically doubled. But once Incogni started scrubbing my personal info, it pretty much stopped being an issue. Actually, come to think of it, how did you find my apartment? How did you find my apartment? Data brokers are able to buy and sell your personal info whether you know it or not. And nothing bad has ever happened because of that. These brokers are required to remove your info upon request, which is where Incogni comes in. It just takes a couple minutes to sign up, and pretty much immediately they'll start sending requests to have your info removed on your behalf. You could do this yourself, but there are hundreds of brokers, which is why Incogni gives you a handy little estimate of how much time you saved by letting them do it for you. That's time you could spend on important stuff, like patching a giant hole in your wall.
I'm the government of USA.
When you're ready to get started, you can visit incogni.com/camwing to get 60% off an annual plan.
Why do you invite me here if you're just gonna do the whole ad by yourself?
I didn't invite you. Take your personal info off the market and directly support the channel while doing it by visiting incogni.com/camwing or by clicking the link in the description. Coming back to Into the Spider-Verse, what I'm about to say should be pretty obvious. The characters in this movie are animated almost exclusively on 2s and 3s. This is the main method they use to make it feel more cartoonish, even though it obviously is rendered in 3D. If they use any interpolation, it's very sparingly. Pretty much every pose was handcrafted 1 frame at a time, like a stop animation movie. In addition to that, they use a lot of heavily exaggerated poses to emphasize the force and speed of emotion. Like in this scene, in a single pose, he goes from seated to standing with his fists raised. He gets a couple poses of wind-up, then on ones, wha-bam, he punches the car and holds it for 2 frames. They added a motion smear, but only to the second one, which conveys a sense of speed when nothing else is changing. But let's go back a couple frames and look at the car. There's a sort of after image of it trailing behind. Those are called multiples, and you'll see them in the next frame when it starts flying away in the opposite direction. You can barely notice these things in motion, it's literally blink and you'll miss it, but all of these little details added up are why it feels so cartoony. Smears and multiples are used to convey movement in cartoons, but most importantly, these same techniques are used in comics, which the Peanuts movie used to very faithfully mimic the newspaper strip it was based on. After winding up, he throws the snowball, but instead of a smear, we get these 2 motion lines, like in the comic. When the ball comes flying back at him, it only takes 2 frames to pass from the left to the right, knocking him in the air in the process. A lot of motion in not a lot of frames. So we've got the same exaggerated posing, motion lines, hand-drawn facial features, animation on 2s, and both movies even use comic book action words. The Peanuts movie was a huge step in the direction of bringing back the sense of cartoonishness to 3D movies, but it still latched on to that Pixar look. The realistic lighting and shading, the simulated hair, the stylized but mostly photorealistic environments. Into the Spider-Verse threw all of that out the window. Lighting and shading are much sharper, textures are exaggerated and messy, they feel more hand-painted. Hair is still simulated, but it reacts to the light like a drawing. If Peanuts was lightly mimicking traditional techniques, Spider-Verse took that mimicry and turned it up a couple notches. But you can still easily tell where 3D and 2D start and end. It doesn't quite blur the lines in the same way that the Great Mouse Detective's clock tower sequence does, but it isn't trying to. The contrasting styles are a conscious decision because they wanted this movie to look different. Both Peanuts and Into the Spider-Verse clearly hybridize 3D rendering with 2D animation techniques, but the reason this one gets all the credit for forcing animation to evolve and breaking the rules of 3D animation is because of what it didn't do. It didn't look like anything else. Hybrid animation obviously did not start here, it didn't even start this century, but when everything else before it kinda looked the same, all it took was for one movie to look like nothing else to make everybody realize, wait, this rocks. Let's start doing that. And then they did. Into the Spider-Verse proved to studio executives that movies are allowed to look like whatever they wanted, and that audiences responded well to taking risks. I mean, not always, but sometimes they do. So, in 2021, Sony Pictures Animation produced The Mitchells vs. The Machines, and since it was made by the same studio, it was made by a lot of the same people who made Into the Spider-Verse, including the same producers and most of the same visual designers, so it uses a lot of the same techniques and animation style, which means I don't have a ton to add here, other than it's really good and you should watch it. But in 2022, DreamWorks released The Bad Guys. 3D animation had always allowed for highly detailed character design, the kind of thing which would have been a nightmare to animate traditionally, but The Bad Guys inverted that philosophy, where characters were designed with simplicity as the goal, like they were originally meant to be animated with pencil and paper. The characters hold on to key poses for longer and quickly snap from one to the other. You'll see shots with backgrounds that look hand-painted, but as the camera moves through them, you can tell that it's stylized CGI. Dust and smoke effects are simulated at a lower frame rate with sharp lighting to look as flat and hand-drawn as possible. Most characters have a set of individual teeth, but when the animators want to exaggerate a specific emotion, they'll swap out the models for a big, toothy grin or an angry, pointy snarl. What makes The Bad Guys look so distinct isn't that they tried to pull elements of hand-drawn animation into a CGI movie, because there's really not a lot of that. It's in the way they integrated classical animation techniques into their 3D animation pipeline. They found a way to make it feel like a hand-drawn cartoon without exactly looking like one. Actually, now that I say that, I guess it's not really a hybrid, but it looks cool. And DreamWorks was on a roll because their next theatrical release was Puss in Boots: The Last Wish, a sequel that nobody asked for to a movie that nobody liked. Aside from the fact that it even exists, the most absurd part is that it's, like, really good. In terms of animation, they went in a bit of a different direction than The Bad Guys, since this is technically a spin-off of Shrek. So instead of upping the cartoonishness, they leaned into a painterly storybook style, where the environments look like they came straight out of an illustration, which is a nice callback to the original movie it's based on. Most of the characters are animated just like any other 3D movie with smooth interpolation, but it's all about the details. Their hair looks like it was scribbled with pencil. The eyes don't reflect light, so they look flat and hand-painted. And certain features are accentuated with line work. But where it gets cool is when the story takes us to an action sequence. It's like a switch is flipped and suddenly the motions are exaggerated with posing on 2s and 3s, with smear frames and action lines. Then once the scene starts to calm back down, the frame rate returns to where it was, like a signal to the audience that things are under control. The movie enters cartoon mode when they fight, and it goes back to storybook mode when things are calm. It's a very cool effect. Peanuts, Spider-Verse, Mitchell's vs. the Machines, The Bad Guys, and Puss in Boots are all very different movies that managed to capture a lot of the same feeling. And that came from the similar ways they chose to mimic traditional animation styles. In an industry where there's a term for just about everything, surprisingly, there isn't a name for this particular technique. But I think stylistic mimicry makes the most sense. The decision to pull traditional techniques into 3D movies feels very new because it is. The goal of blending mediums together was to draw attention to it, to make it stand out. But back in the 80s, when Disney pulled 3D techniques into their traditional movies, they were shooting for what I'm going to call stylistic uniformity, where you don't even realize that the hand-drawn cartoon you're watching has elements of CGI hiding underneath it. Their goal at the time was to blur the lines and ensure that the average viewer wasn't going to be able to tell what parts were rendered in what way. Like Prince Eric's ship in The Little Mermaid. If you know what you're looking for, you can tell it's 3D, but in 1989, it wouldn't have screamed CGI to the average audience member. By the time The Emperor's New Groove released in the year 2000, Disney had really gotten that down to a science. In this scene, Kuzco and Pacha, who are both hand-drawn, were tied to a CGI log, which looks so seamless that I bet most of you didn't notice it was 3D until I pointed it out. They do this with a number of props throughout the movie, and as somebody who watched it over and over as a kid, I'm actually kind of shocked I didn't know about this until now, which means they totally nailed it. In a primarily hand-drawn movie, animation teams will make an effort to uniformly blend 3D animation into it, but the inverse sounds nearly impossible. If your movie is primarily animated in 3D, how would you seamlessly add hand-drawn elements in a way that nobody will notice? Well, that's exactly what Arcane did. Watching this, you would be forgiven for assuming that everything you see here was just stylized CGI, like what these movies did. And the characters definitely are. In the earlier examples, I talk about backgrounds that look hand-painted, but you could tell they were 3D when the camera started moving. But in Arcane, they actually did hand-paint all these backgrounds, and surprisingly, it was done as a cost-cutting measure. As a Netflix streaming series, Arcane has 9 episodes that constitute around 6 hours of animation, where animated movies are usually less than 2, and they don't have a movie budget, so they needed to find a way to make more with less. Shots like this, with the level of detail on display, would have taken a 3D artist weeks to model, texture, and light everything, but if you're only going to see it from one or two different angles, a painter could make static backgrounds with a similar level of detail in just a couple days. There's a really great video that breaks it down quite nicely.
Same thing here, they don't need to 3D model anything here. They just need the painting and project that painting into those layouts. And then they need some shadow catchers so they can later composite with the 3D characters.
In their efforts to save as much time and money as possible, they created a whole new visual aesthetic. Enter Galactic used a lot of the same techniques, but instead of projecting the backgrounds onto 3D geometry, they stayed as static hand-painted images, like what they used to do in traditional cartoons. The main characters are always 3D, but the background elements could be just a moving image. It's hard to tell what mediums are being used and when. Stylistic uniformity is all about invisible blending. The uses of mixed mediums should come together so seamlessly that you either don't notice it's there or it becomes difficult to tell which medium is which. Stylistic mimicry is all about making one medium look like another, but they aren't necessarily trying to mask the fact that it's there. Like, sure, Into the Spider-Verse might capture the feeling of hand-drawn animation, but it's obviously just mimicking it. You can tell it's all CGI. When Moses parts the Red Sea in The Prince of Egypt, the water is definitely computer-generated, but they weren't aiming for a photorealistic simulation. It's stylized and exaggerated, and the effect helps to establish a sense of grandiosity. It feels impossible and miraculous, which is the point. In Atlantis: The Lost Empire, you can tell that practically every vehicle is rendered in 3D, whether they're cars, ships, or a skyscraper-sized submarine. And the different rendering techniques highlight how inhuman and mechanical everything is. It shows off the sense of scale in a very imposing way. It's used to the same effect in The Iron Giant. Having the title character rendered in a different medium from everything else is not only part of the style, it's part of the story, to show how he doesn't belong and why everybody is understandably scared of him. Even though he doesn't fit in the world, he very seamlessly interacts with the world. Klaus does something extremely unique, where the bulk of the movie is traditionally animated, one hand-drawn frame at a time, but it was lit and shaded using 3D rendering techniques. This allows for characters' eyes to have realistic reflections or diffuse light on their skin. They developed a set of custom machine learning algorithms specifically designed to make their cartoon mimic CGI. Insider broke it all down in a behind-the-scenes video that I highly recommend watching after you finish this one. It's some very cool stuff. After Spider-Verse opened the floodgates in 2018, it only took a few short years for Nickelodeon and Paramount to follow suit with what might be the hybridest hybrid movie that's ever been made. I didn't grow up with Teenage Mutant Ninja Turtles. In fact, the only tidbits I ever picked up about it just came through cultural osmosis. Having no particular attachment to the franchise, I can't say I set my expectations for a new TMNT movie especially high until I saw the first trailer. People have accused it of just copying the Spider-Verse style, but those people are stupid. And if you are one of those people, I'm going to prove to you that you're stupid. This movie is animated on 2s and 3s like Spider-Verse, but everything, and I mean everything, looks like it came straight out of a sketchbook. Diffused background lighting bleeds like watercolor. Light sources in view of the camera, like the headlights of a car or an overhead street lamp, use scribbled lines instead of simulated glare. In fact, if I could describe the design motif of this entire movie in 2 words, it would be scribbled line work, because it is everywhere. Particle effects, reflections on glasses or glare from a movie screen, action lines during fast movement. When the camera quickly pans, we don't get motion blur, everything in frame gets scribbly. Fur and hair looks like it was drawn on. But it isn't just the visual effects. The 3D geometry of the world is messy and asymmetrical. There's a very hand-drawn irregularity to all of the models. The handles and vents on these locker doors are all slightly different shapes. The hallway is rectangular, but the lines aren't perfectly straight, and it's like this everywhere they go. Human characters in particular are modeled with an asymmetry to them, like they were hastily doodled in a few seconds. The turtles were raised by their dad to be scared of humanity, to avoid interacting with them at all costs, and most of them are designed with this funky ugliness to them, except for April O'Neil, the one human character who accepted the turtles for who they were and the first friendship they ever formed. I'm not going to spoil anything here, but by the end of the movie, as they gain a better understanding of them, the human characters take on much friendlier designs. It's subtle, but it's a really nice touch. The art style is what drew me into it, but the story is fantastic. I kind of can't believe how much I love this movie. In the way they mimic 2D animation techniques, they were able to uniformly blend everything together completely seamlessly. So I wouldn't stick Mutant Mayhem into the stylistic mimicry or stylistic uniformity buckets, because it's both. The problem with covering such a broad topic is that no single script will ever be able to do it justice. There was a lot more I wanted to talk about. I ended up cutting almost 20 extra minutes just to get this video to a reasonable length. And I barely even mentioned anime. There are some insanely cool examples. If this video does well enough, I'd definitely like to revisit.
Hey, Kimwing,
What's up?
you put smiling friends in the thumbnail?
Yeah? So?
Spend 25 minutes. Why haven't you talked about it?
Oh yeah. I should probably do that. Since I'm apparently in the business of categorizing and naming stuff, there's a third hybrid animation style that you really don't see that often, which I call stylistic dissonance. The objective wasn't ever to blend things together, it was to highlight the contrast between blatantly unmatched aesthetics in the same scene. Smiling Friends is a predominantly hand-drawn cartoon, but they'll regularly pull in different characters from entirely different mediums. You mostly see it used for comedic effect, but if they wanted to invoke a sense of fear, they managed to pull that off pretty well too. Quite a few times, actually. Smiling Friends is legitimately kind of scary on multiple occasions.
Okay, I guess I'll just go now.
They go out of their way to make every mixed media character as distinct looking as possible. Gwimbly looks like he came straight out of a PS1 game, low resolution with jittering Z-buffer and everything. Troglor looks like a PlayStation 6 game with over 1 quadrillion polygons, like a true icon of modern gaming. He's quick, he's smart.
Hey, yeah, no, don't shoot that, please.
But they don't just limit it to CGI, there's a lot of stop animation too.
Living snowman, huh? Alright, I know how to fix this.
Whoa, hey!
If Smiling Friends is hand-drawn at its core, The Amazing World of Gumball is predominantly... Okay, actually, I don't know how they made this. But I don't think there's a better example of a show that smashes different styles and mediums together so unapologetically. The photorealistic environments coupled with 2D protagonists and a wide variety of 3D side characters makes for a series with a style that is truly impossible to replicate. Nothing about this world makes any kind of sense, but that is very much the point, which is reflected in its use of mixed mediums. And I definitely did not take any artistic inspiration from them. The mishmash of mismatched styles shows up in a lot of indie animation as well, like on Deadly Comic.
Okay, I guess we're good. Let's resume wherever we were in the music, and let's go back to Automat. We are skipping irrelevant function and we are focusing on this paint. It's nice because the CPU rendering is actually going to be isolated. Okay, our window, this one, and this is actually a widget, which means it has a shape, which we should be able to find here. The shape is always window-sized, but okay. And I guess each object is transformed in a different way. Yeah, toolbar has one transform and canvas has another transform. Translate 00, yeah, great. Okay, so we should start probably with, let's go back to our rendering process. This. I need to implement all of this somewhere, and since we don't have any good place for that, let's just start writing it here. So first we need this request. This contains a list of choppy drawable ID and the float. Could be a vector. We can just say render times, because we are using float. Float can represent smaller numbers natively. Nice. So this is our request, and we also have a response. I call this packed frame. Packed frame contains two arrays. First, it contains a list of choppy drawables, which will be drawn. And we are working in a multi-threaded environment, so we have to decide who owns things, if we don't want to copy them, that is. But maybe we can copy them, maybe that's fine. Within window, we also have this idea of draw cache. Somewhere here, it should be somewhere here. So this window, when it actually calls drawing, it uses this draw cache object, which is local to the window. And it just contains a list of entries, which are surfaces, render times, and so on. Maybe we won't need that. Okay, we are not doing anything like that. We are not allocating any surfaces. Who needs that? I mean, it would be nice if in the pack frame request we also got some, for example, window dimensions. We will worry about that in a moment. So what we need to do is we need to go through the widget hierarchy, and there was a function for that. So here we have visit children. I think this is what we need to do.
Yashvama says.
Hello.
Hey. Okay, so this is a function that will actually be called multiple times, but only for this single widget, because it can visit a couple groups of its own children. So it's not a recursive function. So this is more like visiting a single node. Okay, so the way to do this, we have to implement a DFS. DFS or maybe BFS? What do we want? I think DFS. And this is our argument.
are you from?
Hey, I'm from Poland. Are you? Never mind. This visitor, we can actually put it even here. So the job of this visitor is to just add the children to the queue. I think there is a way to do it like that. And with this simple trick, we have a draw tree. So in our array, we can have an array somewhere. Okay, so the next step is that we need to find the invalidated widgets. Widgets internally doesn't store much per client state. I think the size of the widget is 8 bytes. I actually paid attention not to make it, not to hold any data in there. So I think the client is going to be responsible. So here we'll have to store the cache. Maybe within the window. I mean, just like we've done here with draw cache. This is where invalidation happens actually. So when a widget gets invalidated, let's see what happens. Exactly, we are going through all of the windows, all of the draw cache entries, and we are marking this as needs refresh. I think we are not going to do that anymore. When we invalidate the widget, we will just invalidate the widget locally. We will not be walking any trees here. So this we will skip. But this is still used. For that reason, I will just introduce a new variable. We'll get rid of them soon. So I think what we need here is this is the earliest invalidation time. Or maybe not, let's just call it invalidation. And let's make it optional. So that when it's not invalidated, we know that it's up to date. We could also use some tricks, such as instead of storing this as an optional which takes an extra byte, actually more than an extra byte. Yeah. So we will introduce a little bit of magic here. I will document this though. So using this invalidated time, we can compute the lag of the value. So if the unvalidated value is before current time, the lag value is current time minus invalidated. If it's after current time, then the lag is 0. Just like we had in this graph here. And this way, it only takes 8 bytes. And this should properly handle all of the edge cases. So if invalidation time, if it was already invalidated, we are not actually going to change this. If it's 0, we are not going to change this, but it's when it's set to like infinity, when it's set to max value, we will then drop it down. Okay, now when we are packing a frame, when we are visiting widgets, and one of those widgets is invalidated, when it's in this state, this is when it should be moved into packing. So within each cache entry, we also need to introduce these dirty or fresh, we can tell this based on invalidation. And the fresh, presented versus scheduled, we may introduce another boolean for that, because those 4 states, they are just 2 booleans actually. So we could have our SK image. So this is our lazy image which we are rendering. So this can be either the presented or scheduled. And those will be different images, and I think even if it's scheduled, it should also have presented. SK image is an abstract base class. These key objects need to be wrapped in this SKSP. We are not using surfaces because surfaces are something that Skia manages locally, and images allow us to create an indirection. Surfaces can also be in this deferred state, but it's harder to transmit this deferred state. In images it's much easier. And when we pack a frame and we send it for rendering, maybe we should always render it like that.
Ratoli says,
Hello, sir.
Hello, Ratoli. And only when we get a response from the client with the render frames, then we will transfer this from scheduled to presented. I'm kind of deep in, so if you want to check this out, rewind to the start. I was like introducing this for like more than 1 hour at the start of the stream. This is a very interesting project. It's a new rendering architecture that we are trying to prototype. So our rendering architecture is essentially going to skip frames for specific objects on screen to create this choppy animation effect.
Ratoli Aegis followed on Twitch.
Hey, thanks for the follow. So when we schedule an image to be drawn, we can also record the time when we scheduled it. And I think whether this is packed or not, we will always send this to this state. Yeah, and when it comes back, we will transition this into fresh and rendered.
Have a good day.
You too. See you around. So this will simplify some things. Okay, but we're interested in this right now, and this we will do only much later on. This will be initialized to null. This will be also initialized to minimum. And maybe we should also store presented time. Maybe we won't need it. Who knows? when we do this packing, I think we will need to create a tree, like a proper tree that we will analyze. We may need to create another vector for that. So my plan is, so after we scan the tree, we should get a list of invalidated widgets with lag and an expected render time. With this list, we will iteratively, we could sort it from the I don't actually remember what's the greedy. Oh no, there was the Wikipedia. There was a greedy algorithm. Should have decreasing order of a value per weight. Then we will go through the list and pick them one by one until we fill the frame. The remaining So to actually have this, so we can compute lag just from the widget itself. So here when we are visiting a widget, we could find the cache entry and check if the widget is, we don't want any scheduled widgets. Not scheduled. Find the cached entry. If the widget was scheduled, then we would continue. If the widget was not invalidated, actually we don't need this max value if we store the presentation time. Actually, when the widget is presented, we should set this to infinity. Yeah. Or maybe not presented, scheduled. The max value is going to be our guardian here. Okay, here we also have this pack frame request with a bunch of choppy drawables. So we should also use that to decide what to do with each widget. Okay, we have to build a tree. So there is a widget here, there is a draw cache entry. You can store it as a pointer. There is a parent. We actually can store this as an index. Not that. So whenever we add stuff to the queue, we should also record who is adding this to the queue. So this will be a queue of pairs. And this parent can actually be encoded as an integer, right? So the root of the tree is connected to it, back to itself, right? call this iParent. And the entry, we should look up the cache entry. Oh, well, I shouldn't be writing here. And this is what I wanted to change. And then I can close. I think I probably should use this constructor. It feels kind of weird. But let's do this. I need to construct this path. So this is not going to work if iParent is equal to 0. I mean, if the tree is empty. Okay, now we have a flat widget tree that we can very quickly scan through. So this is the visit order. If we just go from the back, that would be a topological sort. So in this widget tree we could also store a matrix for each widget, because when we do this visit children, we can also do this. Actually, no, we cannot. Not yet. But yeah, we will be able to do this in a moment, because we are using tree size to get the index of the parent. Can I do this? Without declaring a new variable? I don't think I can. We have this cached entry. Within the entry we also have the render time estimation, this draw millis, yeah, I think I just have to iterate over those widgets. I mean, there is also the thing about combining the result of the previous rendering that we should include now. So a lot of the widget entries will actually be scheduled, and we should transition them from scheduled into presented. Or not. Let's go from the end, actually. And there is a fun structure for that, but I don't want to. I mean, I could say I equals 3.size. Yeah, so there is this kind of loop, which is also, but it can be super confusing to people. think we need to go over the back frame request.
Noah Pombas says,
Hey, look up my portfolio at Noah Pombas. Try I'm a young new developer from Switzerland. Please don't consider this self-promoting. I'm just collecting people's opinion about my portfolio.
Hey,
I know this is not the best way to show off.
sure, I can take a look.
Dang.
And the mouse effect, it is a little bit laggy, I would say. I know this is an animation and that there is this dot following the mouse, but it makes pointing hard. So, if you're kind of looking for a job, I also was looking for a job and also in Switzerland. But the portfolio, I'm not sure if people even look at that. I think what matters, I mean, probably depends. It depends on the company. CV matters. CV, this is like a well-structured document with list of education achievements. This probably also counts. Looks really nice. Okay, one thing more. The image, you've put an animated image. I think it would build kind of more trust if the image was actually a photo of you.
Thank you, appreciate it.
I suppose the image is actually a placeholder, so I guess you're aware of that.
The Evil Root Zero says,
Hola, how it's going today?
Hey, that's pretty alright. We have this crazy cool idea to have this kind of animation. Where was it shown? So, you know, we have lags, right? We have lag issues in Automat. This way around lag issues, and this is to skip frames. So we will skip frames for individual widgets, but we will still composite them at high FPS. So we'll have smooth 60 FPS rendering, but some widgets will just refresh every 2 frames, 3 frames, or however fast they can. But this will make Automat robust to single slow widgets.
But those people.
Something like that. In this animation you have multiple frames which are often stuck on the same image, and this creates this kind of choppy but still kind of smooth animation. I don't think anybody has done this in user interfaces, so we will probably be the first. Maybe some games do this. So, okay, maybe not so first.
How are you planning to determine when to throttle a particular widget?
Ah. Let me find this. You know this guy. This is basically me the whole weekend. I was trying to figure all of this out. I think we have a way to do this. Yeah, so this is the basic diagram for our choppy animations. So whenever we have a widget, the widget is going to transition between a couple of states.
Oh, understood.
So we will try to pack as many, so we will first measure how long it takes us to render each widget, so that we have, when we have a tree of widgets like this one, to each entry we will assign, we already have this actually, we can measure this. If you see, our kind of benchmarking code already does this measurement. It's just we will use this to pack a frame, plan a list of widgets that we will render in each frame. And we will pack them until we achieve, some fixed latency, something like 4 milliseconds, and then we ship this out. Anything that didn't fit in the frame is going to be sent into overflow, and the overflow is going to be rendered in the background. Yeah, so we will schedule all of the widgets, send them out, the client is going to render some of them, and on the next frame the client is going to tell us which frames, which widgets, which textures have finished rendering, and then on the next frame we will composite them. Yeah, so basically if there is any slow widget, only this widget is going to actually render at a slower FPS. So this is similar to the Nagel's algorithm, but for rendering, kind of. We only will re-render widget after we get a confirmation that it finished rendering in the past frame. So this is a combination of so many kind of techniques. So we have this Nagel's algorithm, we have knapsack problem. We could do the full solution, but we are doing the greedy solution because who cares? We have toposort and probably many others, just to make all of this work. It's going to be cool if this works out. Okay. I was just thinking that SK image. I think each image in Skia has a unique ID, exactly. And this is a fun number. Yeah. SK image contents cannot... This looks like just what we need. So basically, we need to go through this list. So let's create step 2. So normally here we would do a hash map. Maybe the hash map would make sense, who knows. We could sort them or something, but actually no, maybe the right way is to just set up a hash map. Does it have conversion to Boolean? It does. Cool. Okay, so if the rendering is finished and it took this amount of seconds, then we will update it. Draw me this. Where do we use that? I mean, sure, we can multiply it by 1000. So here we are updating the render time model. How do I call this? It should be called render time. Okay, let's call this draw millis for now. And this draw millis is going to be part of this section. And now we can swap the presented image with the one that we were rendering in the background. Scheduled image. And we can also do that. And I think this scheduled image should be set to 0. So I will have to check the SKSP. Does this support move? It does. Okay, that's nice. One more check, because I checked the constructor. Okay, assignment operator also supports move construction. Cool. Actually, this is not necessarily correct here, what we are doing, because if we asked the client to render something in the background, it's not going to be presented. I think the client needs to send us two sets, frame render times and overflow render times. Or alternatively, we can unpack them in a tuple and also store a boolean here. You know what, I don't like extra maps, I will just sort this. Our tuple is not assignable, come on. Oh yeah, it's a const reference. Okay, we can do it differently. We can check whether the request was sorted. Why is this API so terrible? I will write my own searcher. Think when low is equal to 0, when high is equal to 1, we'll check 0. try the type of this element. Nice. It's amazing how CLangD can infer the variable times. From this garbage, it managed to figure out that this is a tuple. Nice. Actually, differently, I can do this using the key function. I wonder how does Python do this to avoid allocations. This version with key seems to be worse because actually no, it's not worse, it's the same. For each comparison we have to call this function once. So what's the issue? I think this first type is fairly clean. Maybe I need to specify the second. Yeah. Very weird. This should be deduced. Anyway, so here we have the render time, and the new thing that we now have is the boolean, which says whether this was presented or not. Let's actually name this properly. Let's say this is ID. And instead of tuples, we can now use render results. guys can avoid it doing that. Concepts. I should really learn how to use concepts properly because they would solve this template mess. Let's call this render results. Maybe I will remove this choppy drawable. Maybe we will not need it. That. Okay, so if we actually managed to present this surface, and then we can switch it to this state, otherwise Otherwise, if it was rendered in the background, this is what we are thinking about now. Where is our graph? Like here. I think whatever happened there, I think now we should invalidate like the parent object. If it was rendered in the background and not presented. I think when this happens, we should like invalidate the parent. We should tell the parent that it should composite the next, like this newly rendered frame. Something like that. I think this is already going to be set to null. Maybe presented is the wrong name for this value. Maybe this should be rendered. Because rendered and presented are different things when we are talking about our tree. If things are super slow, then this will render over a couple of frames, then we will invalidate the next object, which will render over a couple of frames, and so on until it reaches the root. Actually, we can do it like that. If it wasn't presented, then we will try to invalidate the parent. Okay, this parent, I think we really need to think about the state of the parent, because the parent can be in one of those 4 states. So if the parent itself is scheduled, then we are not going to present our new image anytime soon still. But that's good, then we should invalidate it. if the parent is in this state, then we actually will invalidate it here. I think this is good. This code here is okay. First of all, if we have any scheduled image, we will continue. Let's put this in a new block. When we are packing the frame, I think this is where we should update the time. Normally window is doing that, probably in the draw function is doing the timer tick. Maybe even here. So if the widget was never invalidated, then we continue. So this is our lag value. How do we construct a duration? I can use a value to initialize it. Cool. I'm thinking whether to recompute it all the time or whether to store it here. I think recomputing is probably the appropriate kind of way to do this. those. I wonder, I guess I need to store them in a separate array because I need to sort this array separately. So each render job has a node in the tree which has to be rendered. It has a lag value. And it has an expected render time. And they are ordered. So I'm hesitant about storing this anywhere because when we pick a render job, where is it? Like here. For example, we pick a render job that contains those widgets. This actually lowers the render time for those which are right next to it. Or for this. So those, basically all of the kind of objects in the graph suddenly can be rendered faster. Okay, maybe I can do this differently. Maybe, no. This is a really tough problem. I think maybe I have to kind of pack the frame right away I can push on this list all of the widgets I would like to render during the frame. I can have a list of widgets which are packed in the frame. I can have a list of overflow jobs. And those jobs that I'm pushing right now, they don't need to be ordered in any specific order. So we can iterate from 0. Okay, first of all, for each widget which doesn't have a surface, it has to be packed in the frame. I should iterate probably slightly differently, but okay. Maybe instead of iJob, we can call it J. Okay, now this is a little bit more complex task than what we kind of do here. Because when we pack a new widget, we should also walk along its parents. And also pack them. This is actually interesting because maybe it's not a good idea to start it like that. Maybe when we start, we should actually draw the widget as maybe we should provide a dummy, like a fake image initially. Actually, that sounds like a nice idea. So the first image will be placeholder, like a transparent texture. Yeah, and then it will appear when it's the time. If this is the case, then we don't need force packing. SK images. Yeah, I'm pretty sure we can somehow render one by one color-based image. So this we will actually not do. So about lag. So we will calculate it like that. Except this render time if we never rendered it, what should we assume? I guess 0, right? Zero is fairly extreme, but I think 1 microsecond is reasonable. Just as a sanity value. Okay, when it comes to rendering a widget, there are actually two things which we should consider. We should consider its own isolated render time, but also the full render time of the widget plus all of its parents. This is what we need to decide whether we pack it or not. So let's initialize this to 0. So when we iterate through the list of parents, we will be summing self-lag, total lag. Or maybe we should take the maximum. We can play with this anyway. Okay, but we should only add this time and bump this lag if that entry wasn't yet packed. So we need to actually record this pack information. Because if this entry was packed, yeah, then we don't even need to follow the chain up to the root. We know that this is going to be our lag. Okay. I will adjust the total render time so it has some reasonable value, and let's call it max lag. Maybe that should be total lag. So after we scan all of the jobs, we should also check the remaining time. And actually, if the total render time is more than the remaining time, then it actually means we can remove this job immediately and push it to overflow, exactly. And could probably swap this job with the last one, remove this, and continue. Let's also include a boolean here and record this. And this is also an interesting case. If one of the parents overflowed, then it means that this widget also by necessity also has to overflow. Yeah, here we will set ancestor overflowed to true. This doesn't matter. Okay, I think we almost have it. We just need to do the actual packing here. So during every iteration, during every iteration of this while loop, we will pack at least one job. Let's actually call this best J. Let's store the job index here so that we can remove it easier. Actually, those arrays packed and overflow, we will serialize them later. For now, I am just going to mark entries as either overflowed or packed. I think we should also decrement J here. Now we should I guess decrease the remaining time. But not only this job should be packed, but also all of the ancestors. Yeah, we pack everything. Okay, I will use this check. Wasn't that bad actually. But I actually think we also have this issue here, so the root object is not measured. So that should be true here. Yeah. We are almost there. I will do some prints so that we can see in console how the packing algorithm works now. So here we should remove this job. Which is actually not so straightforward. I think we should store the jobs differently. So rather having a separate array with a list of jobs, we should probably use pointers in the original tree. Something like that. And instead of jobs, we will have first job. So this is going to be a linked list of indices within this vector here. So now the j is the same as I. Because we are using linked list now, the iteration is going to be, the removal is going to look different. I think we need to store the previous. First of all, we are marking the current job as overflown. This is okay. If the previous is not -1, then okay, this is good. I think this should be enough. Oh yeah. Else, well, Compilot is impressive. Call it best eye, actually. So the removal is still messy because we don't have the previous index. Let's also store the prev job. Double linked list, much easier to work with. We don't need this previ anymore. So this is our removal algorithm. Let's call this I, so that the same code works. This has a good chance of seg faulting somewhere, but it should work. We can actually do the packing. Okay, so we've done this. We didn't then do the sorting. We actually have implemented a pretty decent greedy algorithm, but it takes the shape of the tree into account. It's not the fastest one, but I don't think it will cause issues for us. Those trees are tiny. Okay. So I will temporarily skip this. Probably don't need it. So if we have any of those, then it means we are reusing the image. Let's actually format a nice presentation for this, for our tree here. I will serialize the root entry. So format tree of 0. Okay, so we have this, and we are not going to do the next job. Actually, a tree doesn't include its kind of children. Huh. Whatever, we will do this in a stupid way. Let's see. Okay, we also have to call the packing on every frame. So during paint, let's create a dummy request. We could even call this maybe every 30 seconds, something like that. I'm very curious. Okay, let's give it a moment. Half a minute. Something like that. Oops. What is that? So we have a window and then everything super flat. It shouldn't look like that. Did I mess something up with visit children? Maybe parent. Maybe I didn't specify the parent correctly. Pushback. Yes, I don't think I'm ever changing the iParent to the current element. Essentially that was the issue. Okay, now we got a nice tree of widgets. Window, then root machine, a couple locations, a couple connection widgets, a toolbar. Nice. Okay, actually none of those objects were packed. And I guess this is because actually it's strange because we should be changing the invalidated. Okay, but we are using minimum and we are initializing this like that. Should initialize it to maximum. Actually, no, minimum. Okay, so here okay, yeah, this first job is never set to anything. Another attempt. We should try to pack everything as much as we can. Looks like almost everything got packed. Look at that. Some of the connection widget overflowed. Isn't that nice? Some locations overflowed. This is very interesting. It seems frame packing is doing something. Key presser was packed, but key button overflowed. I also wonder how we should manage the overflow jobs. Say we have this latch list. Let's say all of that overflown. Should we create a separate job? For that and for that and for that. Should the parent job actually use dummy rendering results or the final rendering results? Should we actually arrange them in a tree structure, or should we do choppy rendering here? Maybe let's do choppy now and then we will think. So this frame could actually print how long it takes to render this. Or for each widget actually we could. Let's print some extra values now, so that we know how fast we can render stuff. It should be very, very fast. Oh, I messed something up. Let's analyze this. So window, lag, infinite, render time, 50 milliseconds. Yeah, all of those lag, infinite, because they were never rendered. Some of them have super small render times. But we're still using our minimum here, right? Yeah. So we have infinity divided by something very small, which gives us infinity. So the first render, we really have no good lag information for the first render, so we are just randomly picking some of the objects that we will present during the frame. Using some guess. But that's fine, that's fine. I will make some tea and then we can try doing the next step. And by the way, this looks good. I don't see any issues here. I mean, window overflowed. Because the render time was more than the frame time. But this is because we are estimating the rendering time in a very, very bad way. If I run this again, I don't know, do that. And now it should give us, yeah, much better result. Because now we have a better estimate of rendering time for everything. So now the window was rendering in half a millisecond. It was packed. Root machine got packed, some locations got packed, not all of them. Timeline. Some of the connection widgets were particularly slow, like 8 milliseconds to render. Very consistent, by the way. And the connection widgets which actually have cable displayed, because they need to compile the shader. So this is how much shader compilation takes. That's why everybody avoids it. Or they do everything they can to avoid it. Sometimes it's impossible. Yeah, and we also have those tiny things that are rendered practically instantly. I would say it looks good. I still don't know if this packing algorithm is fully correct because we are just checking these. Yeah, we don't see any interesting scenarios yet. Okay, so in a moment we will take care to actually walk through the widget tree. Or maybe not SK images, maybe SK images. The stuff that we are holding here is SK image, so I guess we have to render this into an SK image and serialize it. This is really interesting that Skia seems to have everything we need. It has so little, but it just happens to be everything we need. So weird. We can follow this step and this step. And this formatting we'll do it like that. Okay, so after we do the rendering into SK images, then we should also click flash the SK images and cool. So be right back. Okay, let's go. So here we are actually packing this into escape picture. It's probably not the way to go. Yeah, I think this should be SK image. There is one more thing we can do to iterate over the tree efficiently. And this is to store. So I'm using all of the kind of tree tricks. So here we have like a linked list overlaid on top of the tree. We can also have a pointer to the first child. And the next sibling. Yeah, and this is something that allows us to actually traverse the tree. And we are still using constant time entries, constant size entries. So this holds a pointer one down, and each of those goes one left. So in addition to parent, we also can have, this kind of navigation. And we could have child count. Right. So it's actually possible to store pretty crazy structures in a flat array. I guess we will go from the back, because we want the images to be stored one after another. And I think there is probably one edge case which we didn't take care of, and this is that the root window, we have to render it. There should be at least one SK image in the frame, and that should be the top level widget. So here, this packing instead of passing this total render time, we should just recompute it. Okay, maybe let's do negatives. That's fine. It means that we have overshoot. So I will do pack 0, which packs the top level frame. And then we are packing the best frame that we found. I will rerun this. Just so we can see, I will not move the mouse so that we get these terrible... Sorry, what's happening now? That was weird. Super weird. The FPS is amazing, but I cannot zoom and zoom. Do I have some overflows? This is definitely caused by packing, right? Oh yeah, it's because of ticking. Because whenever we pack a frame, we call a tick here. I think without this tick it should work nicely. It totally messed up. Like Automat was probably thinking that it's frozen in time or something like that. Yeah. Okay, the window was packed, even though the render time was 50 milliseconds. So, nice. I mean, it wasn't actually that long, it's just... This is our inefficient measurement, which we will fix eventually. Actually, very soon. When we finish this. This is the point where we need to know how large is the object on screen. So here, when we are getting this pack frame request, they should kind of tell us what is the space that we have to work with. That's one. And two is we need the matrix for our object. Yeah. So basically what we will do here is this. I will remove this time measurement, we don't need that. Oops. So we are creating a new recorder, right? We are recording, we have to specify bounds. So we can ask it for its shape or texture bounds, even better. But those are local coordinates. We could include matrices for each entry here. I'm trying to think of ways to actually exploit this situation to get something nice out of this issue. Because maybe I could record it without clip and then I could reuse this recording That's an option. Give me a sec. Spam. We are actually using some tricks here. To render this nicely, we can just try to copy them. But I think should we just use the window size? How did we do here? Canvas bounds. Canvas get base layer size. So this is the same as window size. This animation display, this doesn't include the window size. I honestly wonder what's the width of the window in pixels. We don't have this anywhere. We only have this size here. try some of those tricks, but honestly, I think we should have some information about how many pixels are there in the window. Or whatever, let's just use size and times pixels per meter. So we have canvas bounds. So we are creating this fake context. Next thing we need is root bounds around it. Now we need root bounds. Yeah, let's just get all of this. We are doing essentially the same job here. So we are asking widget about its texture size. If there are no textures, no texture bounds, then it means we don't want to cache the object. Yeah, when the texture bounds are null, it basically means that this widget should actually be merged with its parent. Oh yeah, so this will impact how we render stuff. Yeah, specifically this, the list of render jobs. Essentially, if the widget doesn't want to render itself into any texture, there is nothing we can do to help. So then we say Don't worry, we will just rasterize you. Your parent widget is going to rasterize you. And the rendering time of this widget is just going to count towards its parent. But we have to actually take care of that. I think here we should assert, kind of. So if texture bounds are unlocked, we should really crash. Okay, canvas. Sorry, there is no canvas here. Let's just call this local bounds and root bounds. Okay, time to work with matrices. I was hoping we would avoid it somehow. But when I think about this, we cannot. We really need to understand how stuff is laid out to pack the frame. I noticed we were using parent and iParent, and that was a little bit confusing. Should be better now. So we have to sort the matrix. Where is our tree? Here. So if there is any parent widget, we will ask it for the transform. I hope it's post-concat and not pre-concat, and that I don't have to invert anything. Okay, so this CTM, this is a matrix. That should map, okay, it's named very weird. It looks like a matrix that maps two children, so from a pointer position, for instance. So maybe I have to invert it. Let's look for... Oh yeah, I have to invert it. I'm going to ignore this because this always works. They say trivially inverted, but they actually have some pretty I cannot index the code here, but there is like a proper algorithm for inverting the matrix in Skia. So instead of getting the total matrix, I can do 3 of I dot local to window, because this is the same. Can I even stop this reference? Because I don't think I'm mutating this anywhere. Okay, I am using this SK picture to record stuff. And here we are doing the playback. We will actually not be doing that, at least not right now. Instead, we'll try to flash our animation. Let's look for all instances of flashing. Stream can be flashed. Canvas has some flashing options. Surface has some flashing. This is not what we want actually. Make raster direct. Nope. Nope. Yeah, we actually have to go into a different directory, into the GPU. So there is some flashing here. Here we can flash surfaces, but surfaces are harder to work with than images. They are like GPU space. This is a GPU space concept. So everything else is in this class. So this will flash the whole context. But it doesn't guarantee that the image will be drawn, because the image is not actually rendered on screen, so it can be eliminated from the draw graph. Hey, this is actually interesting. We can actually get a callback from the GPU. Okay, so this is for flashing images and submitting images. But okay, we are not doing this flashing yet, we will do this in a moment. First, we just need to wrap this in an SK image. Speaking of, what facilities for SK images do we have here? SK image Ganesh. Do we have something for SK picture? Nope. Ganesh doesn't care about SK picture. How about graphite? This one actually has something here. Okay, so we have to convert SK picture into an SK image. There's actually very little functions to do this. I think this is the only one. we need to pass the in dimensions, which we have. Those are the root bounds, although the root bounds should probably work on them a little bit. Here. This is before we round anything. So we are essentially checking if this object even intersects with the canvas. Actually, we should be doing this earlier. Yeah, way earlier. So when we are actually flattening the widget hierarchy, this is when we can compute many of these properties already. I'm not sure if we should store it like that. So essentially, whenever we have an object, here, when we are checking if it has texture bounds, this is what we should do. Make more work. So those local bounds, those canvas bounds, I can probably compute way ahead of time. Yeah, so I'm computing the time when I'm taking the snapshot and the rectangle where the snapshot is taken. Hide this packing code, it's not relevant. But this intersection is, so I actually need to compute the root bounds. This widget entry is growing and growing.
Yash Verma says,
Hello.
Hey, hello. Let's check this stuff. So here we are computing the root bounds. So if the object is small enough, I will just check whether it touches the canvas, and if it does, we'll render the whole object. Otherwise, we will clip it to canvas. So I have to move this code earlier, because this is the code which decides whether to reuse a previous image, whether do we actually want to render anything at all. And if the object is not on screen, it doesn't intersect with canvas bounds. Yeah, if it doesn't intersect, we just skip it. Again, we don't need to check that. I should probably install this matrix. I removed it accidentally. Local to window, yeah. Okay, we actually changed the code a little bit so that now it should skip more widgets. Basically things which are not visible on screen, they will not be packed. So we are removing them from the list of jobs. Okay, dimensions are going to be that, root bounds around it. When it comes to matrix, so we are already doing some transforms here. So I'm moving the object a little bit so that it's like perfectly within the bitmap here. So this can be null. Paint can be null. Bit depth. What bit depths do we have? What's the bit depth? And color space, maybe null pointer. And this is our rendered image. This is something that we can actually put in the frame now. I still didn't check whether that was overdrawn or not. Okay, let's start with packed images. Yes. So we are only going to refresh the packed images. I have no idea what to do with animation phases. This is too much for me at this moment. I guess I should do something with them, but I just don't know what. Okay, so when we render an image, and that was an image which was packed, we should probably update some of those values here in the cache entry. So, for instance, I think we should make it part of... We should put it in the scheduled list, probably. Or maybe not. Maybe that was bad idea. You know what, I will remove this presented. And I will change our graph back. So that if something is not packed, we will send it there. But if it's packed, we'll send it to this state. Oops. Should probably do the same here. But okay, we'll think about this another time. So now this is the default. This is never presented. So here is when we do the move. So if the image was rendered, I guess we have to do the same, kind of, almost. Yeah, excluding that. So when we find this image here, so if the currently rendered image is returned from the client with some time, we just need to update the time. We now have a slightly better estimate of how long it takes to draw this. Okay. Maybe it will be good to reuse a little bit of that. Why not? So I'm gonna get the ID of this image, then check if it's on the list.
Ocaladinosaurus says,
How's it going, dude?
Hey. All right. We don't see much progress today, but this is a big project. I think this is what I want to return. A pointer, maybe even. Sure, can be const. I can show you. But I will run the oldest, older build. So we have this tool for playing games, actually. This is, it likes to crash. So this is, if you know Incredible Machines, this is like Incredible Machines environment. but the machines are doing stuff. So some of them will press keys on the keyboard or press the mouse buttons. So if you want to grind some experience or grind some gold
Can you
in a
tell
game.
us a little about the project? What are you working on?
Yeah. So no worries, this is just my TTS getting a little bit delayed. I guess I'm doing some weird stuff, just causing those crashes. But yeah, this is something like AutoHotkey. If you're familiar with AutoHotkey, so this is a more visual interface to AutoHotkey for automating games. I used to play... It's mostly for like grinding games, where you have to repeat some action over and over to get more experience, or to kind of... where the game forces some kind of gacha mechanic, so that you can leave it alone. And eventually it will grind some XP or gold for you.
Yo, cool.
Oh, and it can actually be downloaded. So this actually is released already, since not so long ago, maybe last week, on automat.org. If you insert the floppy disk, you get links for Linux and Windows. This is a very recent development. Okay, so we can move that over here. So, here we shouldn't do anything. I don't know if it's worth kind of creating functions like that, but it sometimes feels like Copilot is just creating so much repeated code that we kind of have to fight against it a little bit. I mean, push it towards reuse. We call this a render time model. With capital render time, the same as in our notes.
You've been sitting on a project for 7 hours straight, man. You're in love with it, or it's an order and the deadline is burning.
we haven't seen any. I'm really waiting to see the effect of this new kind of scheduler. I think it should look cool. So this is something that actually takes slow, choppy renders and actually makes them look nice. Because instead of the whole frame being choppy, it only differs an individual element of the rendering tree. So if you have like a rendering tree like that and only just, one object is very slow, then everything will still be rendered fast, but this one slow object will be just rendered every other frame or every 3 frames, something like that. But it's still going to be composited in a fast manner. Yeah, so I've spent so much time thinking about this, time to implement this actually. And see it in action. Okay, we can hide this. So I was at this point because I think, first of all, let's cache entry. So this is what I am doing. I am actually updating the rendered image, setting this to that. Render time to now. Cool. Yeah.
Ocular Dinosaur just followed on Twitch.
Thanks for the follow. Okay, so we have finished packing the frame and we have actually rendered this. I mean, this is all deferred, so none of this is actually going to be rendered yet. And this is good, because if you have networked clients, we will be able to send them just drawing commands. I guess it makes sense that we actually have to compute the texture sizes and everything here. Okay, so we finished kind of rendering the frame. I think we can add those images into the result. So here we had the pack. And that contains that should be shared pointers. To the frames. Yeah, and we are rendering all of this in the topological order. So the reverse order of the DFS. Now we should go through the overflown objects. And we will probably have to do absolutely the same thing for them. Except this, we are not going to actually update their cached entries. So this stuff, I think we could put this in some utility function. Fairly straightforward. So let's copy this and alter this a little bit. So we are putting this in the scheduled image, scheduled time, we are setting to now. And done. I mean, we just created a response. Now we actually have to execute this rendering. So for each image which we have here, we are not going to do any pix maps. We are going to call this flash and submit. Steady now. Okay, now we need to get the context. The context should have some variable with this context somewhere. I mean, I can get the canvas. Flash and submit image. Can we actually wait for it to execute? Yeah, so there is this submit, which I guess by default is called with not unsynchronized. We kind of would like to have this synchronized. Hey, this is actually interesting. Frame boundary. Okay, I will just call flash and I will submit manually. I can also pass some flash info. What's in the flash info? Yeah, those callbacks. I don't need them. Okay, let's do the manual submit. Ganesh CTX submit. Okay, I could have passed this there, okay. What were my image flashing? Okay, there is no overload like that for SK image. That's fine. Okay, so after flashing everything, then I guess we could try to render this into the canvas. Why are we doing this scaling here? Whatever. Okay. This should render something, I have no idea what. I mean, we are not doing the overflow renders. Probably should. Rear types, something we should fix. Redefinition of canvas, I guess. You know what, I will just reuse this, all of this. So here I am rendering everything in order. I'm doing the scaling the same way. The only difference is here. Let's see. So this will definitely be glitchy. Okay, it crashed even. It's understandable. We're probably doing some weird things. We should probably switch our drawing here. Somehow, I don't know how, but we should do something here. Okay, let's see what's crashing. We are building the debug version. Make surface is null. Step out. I mean, what happened? Did this stop? Yeah, it crashed. I mean, crashed. Even debugger crashed. I just wanted to see the bug trace. Okay, we have an empty image. Nothing is happening here. One thing we are not doing, which we should be doing, is advancing the tick counter. Or maybe Windows was doing that. Oh yeah, but it was doing this here. it's not doing anything on the CPU, and it's not rendering stuff. And we have this classical situation where when you run this in debug mode, it doesn't crash. But why are we not crashing? Was window doing something clever? It did tick, created draw context. It drew some things and then called draw cache clean. Nothing crazy. One thing which is surprising to me is that we don't see the message, which we should see every 10 seconds. Let me try again. I will print this message now. Okay, so this is our frame that we want to render. I don't know why those connection widgets were not packed. Oh, maybe it's because they don't have texture size? Or maybe they were off screen. Yeah, that could have been that. Okay, we didn't even got to image rendering. We stopped. Probably somewhere after printing. Okay, so we have been actually rendering widgets one after the other until we got to window and the window crashed. print one more message, so that just to be sure whether we are returning or not. Yeah, we are not returning from the window rendering. So we are doing something weird here. Camera manipulation. Actually, this could be the threading issues. Whenever we render stuff, we should be doing this on the Automat thread. We still haven't introduced multi-threading. I remember that window actually had some... this. Specifically this run on Automat thread for the actual drawing. It's not a big thing, we can do this. That's not it. What else are we doing here? Stabilize mouse, blah blah. Okay, we are actually doing the draw children here. But when we draw children, this. Then draw children subset, then draw child cached, then draw cached. Okay, so this is probably what's causing the issue. Because now we have these two orthogonal caching mechanisms. The choppy renderer and the local cache. Actually, when it comes to those things, okay, we should not use those. This draw to surface thingy. We should not update the draw cache anymore. This messes up with things. Actually, regardless of whether we are refreshing or not anything. Oh yeah, the surface, that was empty probably. We are only populating the surface here. Yeah, so with the root canvas that we passed to the window. Yeah, it didn't have any surface attached. It was causing issues. This is a very ambitious change, but I think... Okay, the position. We should use this position to render the image. We should get rid of this surface. The stuff that we are not using should be gone really. Hey, look at that, we had a matrix here. Needs refresh, bye bye. Yeah, I actually think this entry could be combined with the tree that we are building here. We'll think about this in a moment. Let's remove the garbage code first. We don't need that. Don't need that. This needs refresh. This code will be useful still, because we have this clip management code here. We have matrix checks here, which by the way, probably need. Yeah, because whenever we render an image, it always uses some matrix that we should store along with this image. Exactly. Here. So this is the craziest trick, which allows us to reuse the old texture to kind of move it on screen. Even if this includes rotations or shears or crazy transforms. I will call this rendered matrix. And I will store it here. Do we use those root bounds for anything? Okay, we are using this for clipping. Okay, we will think about this in a moment. For the time being, we are not really using that for anything. Still very half finished, but I think we are close. I mean, we can hear sounds, right? And I think we are... Are we doing any rendering? How does BTOP look? How is the GPU? Okay, so GPU is doing something. And CPU is just going crazy. Understandably, because we are rendering in a loop without any vsync. Okay, let's remove this noise from here. Okay, I think this is time to put a stop to this for today. We will finish this probably during next stream, because this feels like it's almost working. The big things that we still need to do are this rendering image. Who needs that? Are we actually printing this? Okay, this is actually strange. We are not rendering any images. Just a quick debugger to see what's happening there. Are we packing null pointers? How could this happen? How did we add empty image into the frame? Yeah, it's full of empty pointers. This must have happened here. So for some reason this returns null pointer. Now we can see the escape picture. So picture is there, picture is nice, cool. But then when we create the third from picture, this gives us an empty image. Why? I mean, we can transmit the pictures, that's not a problem, but stop. Let's try again. And let's actually dig in and see where the null is coming from. Okay, this is boilerplate. This is the actual code. Unknown pixel geometry, blah blah blah. Okay. So this is the default constructor for surface props. It's fine. If we don't have any picture, or we don't have the color space, or size is empty, size is not empty. But why is it so small? Okay, for some reason size is 1, 1. Okay, I know why. It's because in our matrix, we didn't apply this scaling that is applied during painting here.
Yash Verma says.
No worries, I will just move this out. Because honestly, I think Window should be responsible for doing this scaling. Here.
Knight says.
I believe that if you applied to Rockstar Games, you'd easily get hired with a high salary. How do you manage to be the kind of person employers are looking for, while also spending time on projects based on your own ideas?
Yeah, I used to work at Google security for like 8 years. In Switzerland, and now I live in a very cheap country. Poland is much cheaper than Switzerland. Actually, give me a sec. I think we need to somehow pass this elsewhere. I don't know exactly where, but this transform, it needs to be included in the local bounds of the object. Back frame. Yeah, so I used to work a lot. And now I have some time to actually work on what I would like to work on. So this I mean, I could do that. Feels weird, but should work. Again, failed to create an image. But now I think we should have some more reasonable bounds. Okay, let's resume the debugging. I mean, I said I would end, but it's... I think we're so close to actually seeing something on screen. I mean, why do you say you crash?
If you received a job offer from Rockstar Games, would you accept it?
Probably not. I mean, it depends. It really depends. Large corporations are usually very flexible when it comes to, you know, project assignments and so on. So maybe. But typically, you know, I mean, I like playing games, I like making games, but I was thinking about Automat for so long. I really want to actually make it happen. This root bounce rounded, this is just killing me. Why is it? I mean, I know why it's so small, but so I have this local to window.
Understand now.
Actually, I didn't mind working at Google. Google was also like I think Google is a very fun place to work. Being in security means that you get to actually like influence people. Like sometimes those are just, sometimes this is no life or death situations even. And like even when it's like not life or death, like the stakes are always very, very high. And it's fun. There is a lot of kind of pressure. There is a lot of like very fast-paced work, but this is what makes it fun. By pressure, I don't mean there is like a pressure to... Actually, the company is very super chill about almost everything. This is probably why it works. But sometimes there are like urgent situations. Especially in the world of security. I'm actually not using the parent transform anywhere. That was the issue.
I used a game company as an example because you do modeling and write in C.
Yeah, and I know a lot of people who work on games. My brother works on games, my wife works on games. So it's like being surrounded. Game development, I think game development is actually the most challenging, the area of computer science. By challenging, I mean it's not like a sport where you try to create like an elegant abstraction for something. No, like this problem is so messed up that you are doing everything you can to actually solve the problem like in the easiest possible way. I think it's really pushing the boundaries of computer science in a lot of ways. I wanted to debug. Okay, I will close this. I don't know why, there are probably different ways to debug this stuff. I really need to click this button for the debugging to work. Check this out. So there is a tiny widget which only takes like 2 pixels, literally. And what widget is actually that? This is 208. I unfortunately cannot check the widget from here. It's probably max nesting level or something. But we probably managed to render quite a few of those images. But actually, if I continue, I can disable this breakpoint and continue. Okay, I'm still aborting. It has to be because of those dimensions here. Actually, does it use left top? Maybe I don't need this translate here. I think I don't. So I think root bounds rounded should do this offset for me. Okay, anyway, we will finish this next stream. It's on Wednesday. We have whole Wednesday, another 8-hour stream ahead of us. Okay then. So see you in 2 days. Bye bye.